Hey everyone, let's jump right into this explainer. Today we're demystifying the advanced pulmonary function test you're going to use literally every single day as future respiratory therapists. We're talking about how to measure the stuff standard spirometry just can't see. We'll be focusing heavily on the big three, the diffusion capacity test, DLCO, along with the helium dilution and nitrogen washout tests. Let's get into it.
Now, as future RTs, you already know basic spirometry is fantastic for measuring vital capacity and forced expiratory flows. But it leaves us with a massive problem. How exactly do you measure residual volume, RV, and functional residual capacity, FRC, when that air never actually leaves the patient's lungs? I mean, think about it. By definition, residual volume is the air stuck in the lung after a maximal exhalation. If the patient can't blow it out, your spirometer simply can't measure it. So, what do we do?
To solve this little mystery, here's what we're looking at today. First, the hidden lung volumes. 2, the helium dilution technique. 3, the nitrogen washout method. 4, diffusing capacity and DLCO. And 5, interpreting the results. All right, section 1, the hidden lung volumes and the limits of spirometry. Like we just said, because residual volume is the air left over after max exhalation, direct spirometry is out. And here's the kicker. If we can't measure RV, we also can't measure FRC or total lung capacity directly either. They're all linked. This means we have to get a bit creative. We need some clever, indirect techniques to measure whatever gas is just hanging out inside those lungs right at the beginning of a test. Which brings us to section 2, the helium dilution technique, our closed-circuit detective. Enter our very first solution, helium. Now, because helium is essentially inert, it's perfect. We can send it right into a closed system to see exactly how much it dilutes within the patient's lungs, and we don't even have to worry about it being absorbed into the blood in any massive amounts. Take a look at this closed, rebreathing circuit here. The patient starts right at their normal resting expiratory level, their FRC, and they just breathe normally into this closed loop. We take the initial volume and concentration of the helium in the spirometer, flip the valve, and just let the patient breathe that mixture. We wait until the helium concentration perfectly equilibrates between the spirometer and their lungs. All the while, CO2 is being absorbed by soda lime and oxygen gets added in to match whatever the patient is consuming. That way, the overall volume stays rock solid. And you know what? The math here is beautifully simple. Since helium is inert and barely crosses those pulmonary capillaries, the total amount of helium we start with is exactly the amount we end up with. It's just diluting into a larger space, the volume of the chamber plus the patient's FRC. So, by taking our initial volume and concentration and then measuring that final concentration, we can easily calculate our one missing variable. Yep, you guessed it, the patient's functional residual capacity.
Now, what does this matter clinically? Well, it's all about the time it takes to reach that equilibrium. A healthy patient, or maybe someone with a small FRC, is going to equilibrate in, say, 2 to 5 minutes. But if it takes up to 20 minutes, that is a massive red flag. Huge. It tells us there's really slow gas mixing going on, typically caused by obstructive lung disease, where air is just getting trapped behind narrowed airways. It's actually a super cool example of the test duration itself, giving you a massive clue about how ventilation is distributed.
All right, section 3. The nitrogen washout method, or as I like to call it, flushing the suspect. If helium was the detective we sent in to snoop around, nitrogen is the suspect we're trying to flush completely out of hiding. And that brings us to our second big volume measuring trick.
Let's quickly compare the mechanics of the two. While helium relies on a closed, rebreathing circuit to reach a nice, steady equilibrium, the nitrogen washout uses a non-rebreathing, open circuit. The goal here isn't to mix gases at all. It's to systematically and completely replace the gas currently sitting in the lungs.
A procedure is actually incredibly straightforward. We're operating on the assumption that the patient's lungs naturally hold about 78% nitrogen, in equilibrium with the atmosphere. So we connect the patient right at FRC, and we have them breathe 100% oxygen. With every single exhalation, they're blowing out that stored nitrogen. We just systematically wash it all out until that peak exhaled concentration drops below 1.5%.
By meticulously tracking the total volume of gas exhaled during the test, along with its fractional nitrogen concentration, the lab computer can use this specific formula to pinpoint the FRC. But here is a critical pro tip. Because this test completely relies on washing nitrogen out, any leak of room air into the circuit is going to cause a grossly elevated measurement. Why? Because room air is mostly nitrogen, so make sure you seal those mouthpieces tight.
Okay, moving right along to section 4, diffusing capacity and DLCO, crossing the barrier. This introduces our final problem. Knowing the lung volumes is awesome, absolutely crucial. But how do we measure how effectively gas is actually crossing the alveolar capillary barrier? For that, we have to turn to our third major category of pulmonary function testing, diffusing capacity.
We solve this puzzle by using carbon monoxide, or CO, in a single breath test. Now you might be wondering, why on earth are we using a toxic gas? Well, it's because CO is literally the perfect proxy. It completely mimics oxygen's molecular weight and solubility, but it has a massively high affinity for hemoglobin. It binds so fast that the pulmonary capillary partial pressure of CO pretty much stays near zero. This is brilliant because it lets us perfectly isolate the actual diffusion of gas across the membrane itself without pesky things like blood pressure variables getting in the way. So during the test, the patient exhales all the way down to residual volume, takes a rapid deep breath of a tiny amount of CO and helium, holds their breath for exactly 10 seconds, and then exhales.
Looking at this equation, the absolute crucial point to remember is that DLCO is simply the amount of CO taken up by the lungs divided by the alveolar partial pressure of CO during that specific 10-second breath hold. And that helium we mixed in? That's there to help us precisely estimate the alveolar volume, making the whole calculation incredibly accurate.
When you're out there in the lab, these factors right here are going to be your clinical anchor. Take a look. Notice how diseases that actually physically destroy the alveolar architecture, like emphysema, or maybe diseases that thicken the membrane, like pulmonary fibrosis, they significantly decrease the diffusing capacity. It makes perfect sense, right? Conversely, conditions that increase the pulmonary capillary blood volume, like congestive heart failure or polycythemia, will actually drive the DLCO up.
Finally, Section 5, Interpreting the Results. This is the big picture. Let's see how all these tests sort of build on one another to give you the ultimate diagnostic picture of your patient. This is the moment where your standard spirometry, your new lung volume tests, and your DLCO all come together to tell a story.
What's truly fascinating here is the physical reality of these diseases when you compare them to a normal lung. Look at how the total lung capacity and the FRC shrink significantly in restrictive diseases like fibrosis. That's from a literal loss of total lung volume. But then look over on the right side. Those exact same volumes massively expand into hyperinflation and air trapping during obstructive diseases, like COPD. It's a night and day difference.
Now, to interpret these reports like an absolute pro, you just need to follow this simple algorithm. First up, look at the FEV1 to FVC ratio. If it's below the lower limit of normal, boom, you have an obstruction. Next, check that total lung capacity. If the TLC is reduced, you've got a restriction. And finally, assess the DLCO to check for any diffusion impairment. Guys, this combination is incredibly powerful. For example, say a patient has severe obstruction and hyperinflation. How do you know for sure if it's chronic bronchitis or if it's emphysema? The DLCO gives you the answer. If the DLCO is totally normal, it's likely chronic bronchitis, which mostly just affects the airways. But if the DLCO is decreased, it points directly to emphysema because that disease is physically destroying the alveolar capillary membrane.
So, as you head out into your clinical rotations and pull up your very next patient's X-ray, ask yourself, which of these chemical detectives are you going to use? Are you going to use the closed-circuit helium dilution, or maybe the open-circuit nitrogen washout to prove they're hyperinflated? Or maybe the 10-second DLCO breath hold to see if those alveolar membranes are still intact? By mastering these tests, you aren't just guessing anymore. You are proving exactly what is happening deep inside their lungs. Keep that curiosity fired up, and I'll see you in the next explainer.